Well, hello everyone. Okay, what I'd like to do today is try to express the following idea, that for someone with a purely procedural programming background, moving into Scala, the best way to learn it is by learning Haskell first, as shown by this diagram. Right, to do this, what I will do is take a walk through 4 key shared concepts that Haskell and Scala have as both functional languages. But before we do that, it's worth discussing why I might want to take this extra level of indirection, this extra step, instead of just simply going straight to Scala. And the reason for that is separation of concerns. Haskell is a purely functional language, while Scala mixes 2 paradigms, functional and objects-oriented. And what that does is it, well, adds a lot of extra mechanics and details that one has to learn, get to grips with, in order to fully utilize it. And to give an illustration of what some of these mechanics are, I'll first move on to the first point on our journey, first-class functions. Right, so in Haskell, this is a function. The syntax places it first and foremost at the front of the language. There are no extra keywords like def, no parentheses, no commas. All you have is the function name and the arguments and then its definition. And this syntax is key to sort of impressing the idea of first-class functions, because each space that you see in Haskell between the function name and the arguments is a functional application, because Haskell functions are curried, a concept that is instantly named after American logician Haskell Brooks Curry, much like the language itself. And what it does, it means whenever you have a multivariate function, you pass its arguments in one at a time. So putting in the first multiplicand into the times function, for example, returns another function that takes the second argument. So if you pass in the number 3, then what you end up is a one-variable function which multiplies its argument by 3. And this partial application provides a certain amount of versatility in situations, for example here, where you want to compose bigger functions from your partially applied one, such as tabulating a list of multiples of 3, in this simple example where we're mapping our partially applied function over the numbers 1 to 10. The equivalent logic in Scala can be expressed like this, but as you can see, the syntax is encumbered with extra keywords, compulsory type annotations, which in Haskell are optional. So if the type of a function is obvious just from looking at its definition, then you can just simply omit that and keep your code nice and clean. Another thing you'll notice is the use of the underscore parameter in order to partially apply the function, which is syntactic sugar for a lambda expression that, again, you can't do in Scala unless you explicitly curry the function like this by putting extra parentheses there. instead of the comma. And in this case, the resultant code after invoking the function does work out to be a bit shorter than the Scala version, actually. But ultimately, what you gain by the Haskell method of doing things is, as stated in the introduction, a separation of concerns. So in Scala, by currying every function by default, you don't have to think about the idea of parameter lists, how to divide up your parameters, whether you need to or not. You just have that out of the box. You also, while you don't have the extra power of the underscore syntax, that again is a separate concern that you can build upon after learning about lambda expressions in the Haskell language first. On our second stop, we'll look at algebraic. Oh, sorry, there's one more thing here. So yeah, if you do want to write it out, as I mentioned, you can put the type annotation of your functions above, like this. And as you can see, the net result is a bit longer than the Scala version. But again, the gain from this is the separation of concerns. You can optionally exclude the type annotation. And this arrow syntax you see up here illustrates the concept of currying. Your function taking a parameter of type n returns another function which takes the second parameter of type n. Right then, so now we'll look at algebraic data types, where for some reason the line is broken after the pipe, but never mind. So we'll illustrate this concept with a binary tree, which in Haskell is very simple to do. You can do it in one line. Aside from the data keyword, all you need is the root type there, and you apply, and your two cases separated by the pipe symbol between the leaf and the node. While Scala, it requires you to define a root type with a covariance annotation. It requires you to define separate cases for the node and the leaf. Again, with all this extra annotation here, which sort of exposes the extra mechanics that get added onto the language by mixing the object-oriented paradigm with a functional one. So again, while these extra syntaxes, these extra annotations are necessary for Scala for what it is, you can avoid them by first fixating purely on the functional paradigm. Right. Next we look at type classes, which are used to provide a new kind of polymorphism that object-oriented programming does not. And that can be broken down into two kinds. There's ad hoc polymorphism and return type. And for our example, we shall try to illustrate the ad hoc kind, which is where you are presented with an existing type to which you want to add new behavior. Now, in a purely object-oriented language without type classes, you can't do that without a bridge or a wrapper class if you want it to extend some kind of interface. For example, explicitly declare that it implements a pre-specified package of behaviors. So what you have to do is create this new class which will implement your interface and then wrap around the previous type. While type classes, they allow you to just simply declare the name of the new behaviors that you want to implement, the type, and what that behavior is. So in this case, it's functors, which represent types that can be mapped over, containers. So what this type signature we have here means is our function fmap, much like Scala's map methods. It takes some function from a type A to B, it applies it to a container of A, and then it returns a container of B. While in Scala, what you have to do is declare your trait, which looks like this. You have to explicitly put in your underscore parameter there to tell the compiler that you're dealing with higher kinded types here, i.e. a type constructor, as opposed to a concrete type. And then you have to declare your function along with parameters here at the beginning, which results in overall not quite as clean a look as Haskell. And moreover, when you want that behavior to be implemented in your class as a method, then you have to define an implicit class in Scala 2, which will automatically convert your type into an instance of functops, which implements that method. While in Haskell, you don't have to consider any sort of concerns about whether the new behavior you want to implement is attached to your type or whether it's standalone and then puts the type in as a parameter afterwards. In Scala 3, of course, this can be done with extension methods, which makes things a little bit nicer because, for example, you can put them in as a top-level declaration as opposed to having to wrap them in an object. But again, there is more syntactic noise involved in that, and by getting to grips with these concepts in Haskell first, you can set aside the object-oriented concerns of attaching methods to your class, and B, you can also spot sort of, well, types which are functors in Scala but not explicitly mentioned as such until you get to grips with libraries such as Scalas and cats. Otherwise, in the standard library, the term functor isn't mentioned at all. All you have is a bunch of various types, future, option, either, list, and so on, which implement a map function, and some of them do implement a common trait, sec, or sec-like, but that declares this mapping behavior, but otherwise all those types, they aren't, well, unified under the functor umbrella until you move on to these other functional libraries, such as Scalas and cats, which do this explicitly for you. Right, and here's an example that implements an instance of a functor on the tree type we looked at earlier. So in this scenario, we're imagining that we're not implementing the tree ourselves, but we are using a library that does so. And it perhaps implements all the usual tree operations like a depth first, breadth first, search, for example, but they neglect mapping behavior, but it is something that you need. So in Haskell, what you would do is you would add an instance declaration in your code, and then do a bit of pattern matching to decompose your tree into its subtypes and appropriately map the leaf or node, and then recursively call your functor mapping function on each constituent branch. In Scala, that's not ideal. Right then, seems to be of a file corruption issue here. What you have to do is declare an implicit value, which creates a new functor. And aside from that, as you can see, there's also extra syntax involved in doing the actual pattern match itself, using the case keyword, for example, as opposed to just putting the match directly in line with your function declarations. Now, for the other type of polymorphism, return type, I won't actually look at any implemented examples, but it's worth mentioning them because it's not something that object-oriented programming can do out of the box. Because object-oriented polymorphism traditionally comes from the ability to extend some superclass. And what that superclass does is it effectively serves as an argument, one additional argument to the method, which belongs to it, because what that method does is it uses properties of that class in order to compute its output. But you can't turn that around and say your method returns the class which is exhibiting this behavior. But type classes, they do allow you to do that. And we'll see some examples of why this is useful here. So the first example we'll look at is read. Again, Haskell code here. And what that effectively represents is any type that can be passed from a string. So the type you're instantiating as readable is R here. And it just declares the single function read, which operates on a string. And you won't be able to get this from an object-oriented method because you can't attach a method read to a string object and then have it return any arbitrary type that's inferred from the context in which it appears. But Scala, type classes in Haskell and indeed implicits in Scala allow you to do this. A prominent example of an analogous case is the JSON reads function from Lightben's Play library. So reads is a type class which allows you to pass arbitrary types from JSON, provided, of course, you implement the appropriate read method for it. Another kind of return type polymorphism is in nullary functions, functions that take no arguments, which in Haskell are equivalent to constants, because a nullary function that isn't constant would violate referential transparency, i.e. the principle that you should always be able to determine the output of a function from its inputs. And we can see an example of these nullary functions or polymorphic constants in the bounded type class, which has the constants max bound and min bound of the type that is bounded, and can be seen in things like, well, your basic integer, byte, short, float, double types, because you have a limited amount of memory with which to express them, so they naturally have upper and minimum bounds placed there. And in Haskell, such primitive types, they are instances of this type class. Now, I was talking about referential transparency earlier, and the fact that a constant can be polymorphic might sound like it violates it, because, well, how do you determine the what value it is if it can have multiple forms? And the answer is through context. Its type, its value is determined at runtime through a Haskell's Hindley-Milner type inference. That's something that might be worth looking up if you're interested. And what it does is it basically means that whenever you place your max bounds or min bounds into code, the type inference algorithm will infer them from their context. For our final example of return type polymorphism, I would like to mention the monad, which is another key concept in the area of functional programming. First of all, let's talk about the polymorphic return type, which is in the return function. What that does is it takes any arbitrary value and then it wraps it in a monad. The other method that you have to, function in Haskell that you have to implement is this operator here, which is called bind. And what that does is, it's like the functor's map function, except it also flattens the result. What this means is it takes a function that operates on a pure type, returns a monad, but if you were to map this function on a monadic type, then what you would end up with is a stack of monads, a monad wrapped around another monadic type. And, that adds extra context that you don't need. Say we look at the simplest example of a monad, aside from the identity, the option. If we're trying to coalesce a sequence of operations which might potentially fail, and we just map over them, then what we'll end up with is nested options, one inside the other, and this is redundant information that we don't need only to understand whether or not the ultimate computation has succeeded or not. So what we do is we flatten this stack, and the bind function, which the monad type class implements, does that. It combines the functor's map with a flattening operation and reduces your chain of operations to one which doesn't produce a stack of monads nested inside another. In Scala, the code for doing so looks like this. And you have to call the return function pure because, return is a keyword in Scala, and below you have to implement an implicit conversion to apply the bind operator as a method. Now, when it comes to monads, what Haskell does for you isn't so much a separation concerns, I would say, as something which builds your intuition for encountering similar data structures in the Scala language. As I mentioned before, functors, they don't really explicitly crop up in Scala until you use functional libraries, such as cats, and a similar thing is true in Scala. you don't have a monad type class as such in the standard library, but you do already have many different types which act like monads, namely options, ethers, lists, and futures, for example. And what learning Haskell first did for me was, well, make it obvious, explicit to me that these types, they're all monads. And what that meant was, when I moved on to Scala from them, even though I wasn't working with functional libraries, whenever I had to deal with these types that behave like monads, I could easily recognize it. A simple example of how this helped was whenever I would look at people's concurrent code and they would flat map a future.successor onto another future. That's just equivalent to mapping whatever's inside your future.successor to the future. You can simplify that code, and the intuition that the functor's map is just equivalent to a bind composed with a return is something that you gain by learning Haskell first, but that might slip past your radar if you rush into Scala first. And well, that's about it. Aside from maybe full comprehensions. Full comprehensions are another area with which learning Haskell first helps, because they are equivalent, because they are essentially syntactic sugar for chaining flat maps. And that is the same as what Haskell's do syntax does. And yeah, as I mentioned before, with futures not being explicitly implemented as monads in Scala, them being monads is something that I might not have otherwise understood until I was working with Akka, and I suddenly realized, hang on a minute, this chain of futures that you're for comprehensioning with, it looks suspiciously like a sequence of binding operations. And that was when it clicked for me that they are monads. A similar thing happened when I started working with Scala check and its generators as well. You build generators from other generators by composing them, and sometimes you might want to apply a function which builds a new generator from a generated value. Now, if you map that function onto a generator, then what you will end up with is a generator of a generator of your required value. And monadic binding, or flat map as it's called in Scala, it encapsulates the flattening of this operation. And by seeing examples of how generators are composed using for comprehensions, I was able to recognize the fact that they are monads and more intuitively work with them. And that essentially sums up perhaps what learning Scala after Haskell did for me. Allowed me to compose object-oriented concepts on top of functional ones, much like the functional concepts themselves help you easily compose code. What it did for me was it allowed me to grapple with the functional concepts in isolation with their clean, expressive syntax, separating all the extra concerns that object-oriented programming applies on top of that, such as variants and implicit conversions, or extension methods, as they're called in Scala 3. And that is how I became a Scala programmer. And well, I'm hoping that this gives you a little bit of an idea of how perhaps if you're trying to mentor junior devs in the functional style in Scala, how it might potentially help you illustrate the functional concepts in a cleaner, purer environment, or perhaps it might even help you better get to grips with concepts yourself. But either way, well, I hope I give you something to think about on this topic. Thanks for listening. If you have any questions, I'll happily take them, because, yeah, if anything there wasn't clear, if anything needs to be elaborated on, I would love to do so. Yeah?
Do you think that these insights would be generated if you had learned any functional programming language, or is there something specific about Haskell that you think generated these?
That's a good question. I would have to dive a little bit deeper into the history of programming languages to be sure of the answer to this, because I know, for example, that Haskell syntax was heavily inspired by Miranda. So I suspect that learning Miranda would give you a lot of these insights as well. But type classes, the polymorphism that they give are, if I recall correctly, something that debuted in the Haskell language. So I think for that purpose, learning Haskell would probably be better, if I am correct on this point. But again, we'd have to check on that. Yeah, anything else? Yeah?
How long did it take you to learn Haskell?
That's an excellent question. So I first started learning it when I was 18, and I blasted through this book called Learn Your Haskell in a matter of months, maybe weeks. I thoroughly enjoyed it. It was, unironically, a real page turner, because I really loved the way it changed my way of thinking, completely expanded my outlook on the concept of programming as a whole. But yeah, actually getting fully to grips with all these concepts was something that happened over the course of many years, I would say, because even though that book introduced me to monads, it gave me plenty of examples for them. All those examples did to me was serve as a foundation to eventually intuit monads better when I later encountered them. And when I encountered them, that often happened years later, such as with a future monad when I was working with Akka a long time after that. So I would say that, yeah, it happened in starts and stops, the learning process, over the course of many years. Some bits very quickly, then there's a lull, and then suddenly new intuition comes along, bam, when you discover a new library. Yes, it's hard to measure.
Okay.